All right, in this second video on hypothesis tests, we're going to define a bunch of terms that we use in hypothesis tests in more detail and really unpack the nitty-gritty of how hypothesis tests work and what the key concepts in them are. So the first concept that we need to focus on that comes up in step one out of the 4 steps of a hypothesis is the null hypothesis. The null hypothesis is a statement about the population, usually about a population parameter, saying that it's equal to a precise value that will be used as a benchmark that the data will be compared to. Again, in our last video, we talked about the example of using 0 as a benchmark for the difference between how children scored on the 2 types, or the test under the 2 types of conditions. So often 0 will be a benchmark that we use for this, but the benchmark could be anything, just some baseline that we want to compare things to. So a few examples. Population and population A and population B have the same mean. That would be a very common benchmark. In other words, we would be saying the difference between them is 0. We could also say that there's no correlation between variables x and y in the population. In other words, that the correlation between them is equal to 0. Again, one of the key ideas of the null hypothesis is that it's saying that some parameter is equal to a precise value. Here it would be the correlation between these and the population is equal to 0. We don't want a range of values. We want it to say that it's equal to a precise value for the null hypothesis. Maybe if we're thinking about SAT scores and I want to think about how my district compares to the rest of the country, and I know that the national average to score on the SAT is 1,000. This is maybe using an old metric for the SAT. They may have updated it since I took it. But if the average SAT score is 1,000 across the country, it would be, if I'm trying to understand my district, one of the things I might care about is where do I stand relative to the national average? And so a natural baseline to compare things to might be 1,000. So I could set up a null hypothesis that says my hypothesis is that the SAT score in my district is equal to 1,000. And I put true in quotation marks here because, of course, I can just check what the SAT score in my district is. But the SAT score is going to bounce around somewhat from year to year and might change depending on which students take it and whether or not they're feeling well the day that they take the exam, whether or not they happen to get lucky that day. And so when I say the true SAT score, I'm thinking about maybe I have several measures of how my district does on the SAT, and I'm trying to think about, well, what would they do if we took away all the statistical noise? Would it be equal to 1,000? Would it be higher? Would it be lower? So for the null hypothesis, though, I don't want to say higher or lower. I want to identify a precise value. So my null hypothesis might be that the true average SAT score for my district is equal to 1,000. Usually the null hypothesis is going to indicate that there's no effect. So for example, that there's no difference between groups, or that if we have some intervention, that it doesn't make any difference. If we have a medicine that we're testing out, that it doesn't affect people's health at all. Or that, if we're looking at outcomes among 2 different groups or between 2 different groups, that the outcomes don't differ at all between those 2 groups. That would be a typical null hypothesis, even though you can write null hypothesis lots of different ways. We use the null hypothesis as an assumption, technically, and then we test the feasibility of that assumption based on the data. That's the way that statisticians use null hypotheses when they're creating equations to be able to let us generate a p-value. But that's a little bit of a technical explanation of what the null hypothesis is. Intuitively, what we're doing with a null hypothesis, whenever we run a hypothesis test, is we're asking the question, is the null hypothesis believable given the values that we found in our sample? Remember, the null hypothesis is a statement about the population. And so we're looking at our sample and saying, based on this sample, is it plausible to believe that this is true about the population, that whatever the null hypothesis says is true about the population? All right. The alternative hypothesis is also something that we're going to write in step 1 of a hypothesis test. And the alternative hypothesis is simply going to be the logical alternative to the null hypothesis. Now, we're going to put a slight caveat on that in a moment, but that's at least a good starting place, is to think about the logical alternative to the null hypothesis. So if we look at some examples that would correspond to the examples we just saw of null hypotheses, we would say that population A and population B have different means. If you'll recall, the null hypothesis on the prior slide said that population A and population B have the same mean. Notice that the null hypothesis is very precise. It says that they're exactly the same. In other words, that the difference between them is exactly equal to 0. The alternative hypothesis is much more open-ended. It's saying that the means are different. Population A could have a higher mean, population B could have a higher mean. The difference could be 5, it could be 10, it could be 20. It's just saying that the difference is not equal to 0. So it's much more open-ended. Similarly, if we're talking about correlations, we had a null hypothesis, the correlation in the population between X and Y is 0. Here we would say, as an alternative hypothesis to that there is a non-zero correlation. In other words, there is some correlation. It might be positive, it might be negative, but there's some correlation between those two variables. Again, if we're talking about SAT scores and thinking about how my district compares to the country, an alternative hypothesis would be that my district's true average ACT score is greater than 1,000. Notice that in this case, I do specify the direction that I think it's different. We'll clarify that in just a moment. I could also write a different alternative hypothesis that would just say that my district's average SAT score is different from 1,000, but here I've decided to specify greater than 1,000. That's still quite open-ended, though. It could be that my district is 5 points better. It could be that it's 20 points better, that it's 100 points better. I don't really give a very precise statement in my alternative hypothesis ever. So, while the null hypothesis is very precise, the alternative hypothesis is going to specify a range of possible values. And there's actually two types of alternative hypotheses, which I've already alluded to. So one type of alternative hypothesis that's a little bit less common, I would say, is a directional or a one-tailed hypothesis. And that is something like saying that the population correlation is greater than 0, as opposed to a two-tailed or non-directional hypothesis, where I would say the population correlation is different from 0. So notice that with a two-tailed or non-directional test, it could be that population A is greater than B, or it could be that it's less than B. It says that this difference could go in either direction, whereas the directional or one-sided hypothesis is going to say something a little bit more precise. It's going to say that the truth is greater than the benchmark or less than the benchmark. That's what we mean by these two different types of alternative hypotheses, a one-tailed or a two-tailed. It turns out that how we write the alternative hypothesis, whether we write it as a one-tailed or a two-tailed test, is going to affect the p-value that we get. So that's why we care about this distinction, although it's not going to be a major focus of this course. It is something that's important to be aware of for this course, though. All right. The next big concept we want to talk about is the alpha level. The alpha level is one of the more abstract concepts in a hypothesis test, but basically it means the threshold that we're going to use to decide at what point a result is unlikely enough, our data from our sample is unlikely enough if the null hypothesis were true, that the null hypothesis needs to be rejected. Like I said before, our default value for this is usually going to be 0.05. But let's talk a little bit more about what this alpha level means intuitively. So remember that in hypothesis testing, we're thinking about whether the data we've collected in our sample would be unusual to observe if the null hypothesis were in fact true. So for example, let's say that I'm thinking about whether or not the true population mean might be 1,000. My null hypothesis is that the true population mean is equal to 1,000. That's my benchmark. If that were true, we would expect that getting a sample mean of 998 would be much more likely than getting a sample mean of 800. That's because, as long as at least we've used random sampling, we expect that our sample is going to be more likely to give an answer that's close to the truth than an answer that's really far away from the truth. And we kind of saw that when we looked at sampling distributions, right? The sampling distribution is going to give us some sort of normal looking curve, but it's going to be centered around the truth. In other words, the values that you're most likely to get in your sample are going to be values that are close to the population parameter. At what point, though, do we decide that our sample data is so unlikely under the null hypothesis that we conclude the null hypothesis must be false? The alpha value is going to be a way of representing in numbers what that threshold should be. Um, so when we're thinking about choosing a threshold, there's a trade-off that we face, and this trade-off is a bit complicated to explain. So there's a lot of pieces to keep track of, but you'll get a chance to practice these concepts in the coming weeks. So first of all, one option is to have very little tolerance for unusual data. In other words, if the sample looks just a little bit different from what we stated in the null hypothesis was true of the population as our benchmark, if the data differs just a little bit from that, we're going to reject the null hypothesis. That would be one approach. If we take that approach, then we have fairly high odds of incorrectly rejecting the null hypothesis, assuming that null hypothesis was actually true. The problem is we don't know at the outset whether or not the null hypothesis is true. So we're having to guess, and we're having to think about, well, if it's true, what risk are we taking? If it's untrue, what risk are we taking? So that's how we think through this. If we use some technical jargon, we can say that a larger alpha value, for example, picking an alpha value of maybe 0.3, 0.4 instead of 0.05, a larger alpha value increases the risk of what we call a type 1 error or a false positive. Those are other ways of saying that we reject the null hypothesis even though it's true. Of course, that can only happen if the null hypothesis happens to be true, but we're asking the question, if the null hypothesis is true, how likely are we to incorrectly reject it? The alpha value is going to tell us how conservative or willing to take that risk we are. If we have a lot of tolerance for unusual data, in other words, if we're going to say it takes a lot of evidence to convince me that the null hypothesis is false, we're going to have fairly high odds of failing to reject the null hypothesis, even if that null hypothesis is actually false. So in other words, we're going to reach a lot of inconclusive results in the case that the null hypothesis is actually false. So using sort of the statistical jargon, we would say that a smaller alpha level increases the risk of a type 2 error. And this is something that we'll come back to and we'll explain again. On the next slide, I believe it is, we'll actually have a formal definition of type 1 and type 2 errors. So in real research, of course, we never know for sure whether or not the null hypothesis is true. So the main point I want you to take away from this slide is that we're doing a balancing act, right? We're trying to decide how much risk we take of maybe failing to reject a false null hypothesis versus maybe, if the null hypothesis happens to be true, accidentally rejecting it even though we really shouldn't have. And in the real world, when we're using hypothesis testing to do something like make a business decision or a decision for a government policy or something like that, we want to try to think about weighing what the risk of being wrong would be in each of those directions, right? We might have more tolerance for one type of risk, a type 2 error versus a type 1 error, depending on what the consequences would be of being wrong about the null hypothesis in either direction, either saying, well, maybe it's true when it's not actually true, or saying, yeah, we think it's wrong when in fact it actually was true. So those are the two types of risks that we're trying to weigh. We'll have lots of examples of hypothesis tests throughout the rest of the semester, and so we'll get lots of chances to think about what having a higher or lower alpha level means. Right now, we're just trying to explain the theory in this video. So technically, if we want to give a formal definition of the alpha level indicates the probability of getting a type 1 error if the null hypothesis happens to be true. Of course, if the null hypothesis happens to be false, we can't get a type 1 error because a type 1 error is saying that we rejected a null hypothesis that was true. So if the null hypothesis happens to be false in the real world, which we can't know ahead of time, then we would never commit a type 1 error. We would only commit a type 2 error. So an alpha level of 0.05 means that there's a 5% chance of getting a false positive if the null is true. And the default alpha level usually is 0.05. So at this point, you don't have to think for this class too much about how you're going to pick an alpha level. You can just use 0.05 because that's typically what social scientists use. But I do want you to know that there's a trade-off that we're facing, and I want you to be able to pick out the difference between a type 1 error and a type 2 error, just like I want you to be able to pick out the difference between a one-sided and a two-sided hypothesis test, even though I'm not going to expect you to necessarily make that choice a lot in this class. Other common levels that sometimes get used by social scientists or other types of scientists would be 0.10, 0.01, 0.001, depending on how certain people want to be that the evidence lets them or compels them to reject the null hypothesis. So sometimes you'll come across studies that use other thresholds besides 0.05 for the alpha level. All right. A few more definitions. Statistical significance. You might have heard this term. It gets used in the media sometimes. Statistical significance, that just means that the null hypothesis got rejected in a hypothesis test. A lot of times people use this term without specifically describing all of the steps of a hypothesis test, but they implicitly are referring to some sort of hypothesis test. So if someone says that the correlation between these two variables is statistically significant, what they mean is that if you had a null hypothesis that there was no correlation between those two items, you would be able to reject that null hypothesis, probably under an alpha level of 0.05. An example of how people use this term is that somebody might say the difference between two sample means is statistically significant, which would indicate that when there's a null hypothesis of the means being equal, that null has been rejected. The other two definitions that are important for you from this slide are a type 1 error and a type 2 error. And again, we already went over this on the prior slides, but a type 1 error is rejecting a null hypothesis that is actually true. Sometimes we also use the term false positive to describe a type 1 error. And a type 2 error is a failure to reject a null hypothesis that is false. So when we think about this in the case of studying an intervention, and maybe we're doing a randomized control trial to, for example, see if sending clients an email to remind them to come into the office for some sort of appointment or something like that, if we want to know if that makes them more likely to show up, if we're doing a randomized control trial to see does sending that email or that text message cause people to show up more, our null hypothesis would probably be that the email or the text message has no effect. And if we had a type 1 error, that would mean that in reality, the message had no effect, but we made a mistake. We accepted a certain risk that we might be wrong with our conclusion, and we were wrong. We said that the email had an effect, and it didn't. That would be an example of a type 1 error. A type 2 error would be the opposite. That would be we run our analysis and we say, oh, we can't conclude that this had any effect, when in fact it did have an effect. And when we set our alpha level, again, if we set a really low alpha level that's saying we need a lot of evidence, that means we have a high risk of a type 2 error of concluding, well, we're not sure, even if maybe the intervention did work. If we have a really high alpha level, maybe an alpha level of 0.4, we would be saying, we don't take very much evidence, we don't require very much evidence at all to conclude that this message had an effect. And that increases the risk that maybe we're going to say the message had an effect when in fact it really didn't. That's what we mean conceptually by balancing that risk between type 1 and type 2 errors. All right, that's it for this video. In the next video, we'll look at one more example.